Um, Tushar, maybe go ahead and get started.
Yeah,
Introduce yourself.
yeah. Um, Great. Let me just make sure my mic is on. Great. Um, Hi everyone. Really excited to give this talk. I'm Tushar Jois. I'm an assistant professor at the City College of New York in the CUNY Graduate Center, and I'm really excited to tell you about my research on Thrifty MPC, reducing the cost of large-scale MPC in the cloud. Now, this is joint work with a number of people, and let's get started. So today my talk is about people, or at very least motivated by people. We're all human, but we all have slight variations in our genes that are expressed in our individual characteristics. People are not perfect clones of each other. And this is relevant from a healthcare standpoint. An important relationship in medicine is this idea that there's a relationship between the genetics of a person and the diseases they may have. And if we can associate characteristics from a human genome with the diseases a person has, we can identify markers for diseases, right? And this can help aid us in diagnostics and testing. If we know what gene mutations to look for, we can maybe figure out what diseases a person may have. So this has led to the rise of genome-wide association studies in the bioinformatics literature that take a wide sweep of the population, attempt to identify genetic markers, and develop testing based off of it. So a genome-wide association study, or GWAS, goes as follows. A group of people have their genetic data collected somehow, and this genetic data is aggregated and analyzed by a university or healthcare institution. And this results in the publication of papers that have some information on the population and potential diseases and potential markers. And this potentially goes back into therapies, which is really exciting. Now, a result of a GWAS is only associated with that population. So if I want to understand more about a specific disease set, I may have to recruit another population, get their genetic data set, and then perform the analysis. And this goes on for several other populations and data sets. And you can kind of see by this layout here that this results in a relatively siloed set of tests, right? There is no aggregate view of the entire population. The individual results are kind of confined. And if a disease is particularly rare, for example, it only shows up in the purple group, it might not show up in the blue group and the green group. And there may be some interactions between here that are not being expressed. So we're missing things. So it's important to be a wide collaborative spread of people to get the best possible outcome. So we really want collaborative GWAS, right? Collaborative genome-wide association studies. And this is something that the bioinformatics folks are trying to build out. And they're trying to do this in two primary ways. The first is cross-institutional agreements. And this is the most obvious way of trying to do this. They're essentially contracts between the entities that hold these data sets. So multiple universities have data sets and they try to come together with contracts to make sure they're not misused. So they specify some sort of policy as to how the data should or shouldn't be used. And then essentially they use the legal system to enforce behavior, right? The threat of legal penalties is preventing people from misbehaving, or that's at least how we're thinking about it. So, the interesting thing here now is, it's very time consuming. If any of you have tried to get an IRB before, you can know that it's actually very difficult to put together an agreement that will satisfy all the university priorities and policies. And doing that across institutions, that means you have to satisfy more constraints across more parties, which is hard. Another thing that's hard is that it's just simply hard to enforce, right? If there is some kind of issue, you have only a legal remedy, and legal remedies are possible, but they are slow and they require some effort, right? You need to have lawyers and have them spend time enforcing this. And this also will require some funds. There's also an interplay with other related laws in like HIPAA that are actually provided by the government, and regulations provided by the government. You need to make sure that all of your agreements satisfy all of these properties within the legal system. And then I think a big thing that is often missed by this institutional agreement setup is human error. Often the big enemy is not actually people misbehaving maliciously, it's just them misbehaving on accident. They accidentally keep data on a server that they're not supposed to. They accidentally forget to delete it, right? And given how sensitive this data is, we really want to avoid this kind of human error. Indeed, one of the collaborators on this paper is a bioinformatics professor. She's a genomicist. And she actually told us that these agreements are hard to get. And the fact that these agreements are required is slowing down collaboration significantly. On the other hand, the alternative is to use summary statistics. We don't provide the actual data, but we'll compute some summary statistics over them and publish them. You get some high-level information about the data. It's useful for validating experiments between data sets, kind of compare how the data looks. Now, it does that without maybe leaking specific information about the individuals in the data set. And this, if you're familiar with differential privacy, has kind of that flavor to it. It's not as useful, though, as actual test results because you don't get to go into the data and make comparisons and really drive into why certain things are the way they are. They don't necessarily support this collaboration that is necessary to achieve really deep rare disease studies, really deep insights. So now we come to the age-old question, what if we throw in some cryptography? And now it might be more clear why I'm presenting this work at this seminar. So what if we throw in some cryptography? What cryptography can we use? So today we'll take a look at secure multi-party computation, which is a cryptographic protocol, or a set of cryptographic protocols that allow you to collaboratively compute a shared functionality. And you only know your own inputs as they go in. You don't learn the inputs of other parties. In fact, you only learn the output that you receive and whatever information can be inferred by them, right? If you receive some, let's say, average value, you'll only understand, something related to other people's data based on the average. So it's a very powerful tool. As a visual, here are three parties. They each are going to get some kind of output. They each have some associated input that is processed to get this output. And I want to point out that these outputs can be the same. They can all receive the same output, or these outputs can be specific to the individual parties. Now, in secure multi-party computation, we typically have a threshold assumption. So here, let's assume a 2 out of 3 protocol. What is a threshold 2 out of 3 protocol? Well, if you assume that all 3 of these parties are honest, you will get a result. You will get the actual result. If you assume that 2 of them are honest, then you will also get a result, 2 out of 3. But if you have 1 or fewer be honest, then you will not. The protocol will stall and fail. Now, this has implications for the adversary model. They need to control 2 out of 3 of the nodes to unlock the secret values in the protocol. This means that it's more work for an adversary to kind of take over, which is a useful property. So it kind of seems like we have a solution, right? Each party will participate in an MPC, and we will just submit our genomic data that we have locally at our institution as input into the MPC, and then compute a function between each other over a cryptographic domain, get our output, and we're done. So there's our solution. The talk is over. Everybody go home. But not quite. Because now that we're talking about the interplay between cryptography and real applications, we start to encounter some challenges. Now, a lot of modern computation, including data science, is done on public clouds. You've probably heard of these. Amazon has AWS, Google has their cloud platform, Microsoft has Azure, right? These are pay-per-use services where you can use cloud computing. Now, data science and genomics have a particular interest in cloud computing because much of data science is worldwide, right? There's an advantage to using these public clouds if all of your parties are distributed geographically. Now, these parties aren't distributed geographically for any arbitrary reason, right? These institutions have data for local populations. So if you want to do a collaborative study across multiple populations, you need to have more people involved, right? Data centers are also geographically distributed, and they have good connectivity around the world, right? These companies, our bread and butter is making sure that they have good interconnect. So in this way, you can use a centrally located cloud provider, a centrally located instance or data center, essentially, to compute your data science or genomics tasks. So in addition to this geographic thing, there's also the nice thing that cloud computing supports nice scaling properties, right? If you're an institution and you need more CPU or RAM for your workloads, this is vertical scaling, you can simply just pay for a new instance that has higher amounts of resources. Or if you need to purchase more instances, you need to want to parallelize your workload, you can do horizontal scaling very easily. And it obviates the need to maintain any sort of local hardware, right? An institution doesn't have to have all these beefy servers. They all the time and maintain them and hire IT for them. They just need to pay for the specific uses, the specific time that they're running them. Now, despite all these advantages, public clouds have their costs, like literal costs. They cost money. And human genome data is very large. It's exceptionally large scale. Some even consider it more large scale than astronomical data. So this means it costs a lot of money to do genomics on these public cloud platforms. And indeed, individuals in the bioinformatics community are starting to sound the alarm. They're trying to identify how cloud costs can impact the GWAS pipeline, right? So these are not computer scientists necessarily, right? Or systems researchers or security researchers. These are actual bioinformatics researchers who want to reduce their cloud costs. So genomicists are actually starting to build their own cloud architectures just around reducing costs. So it's clearly of interest to their community to keep costs low. And it's really hard to reconcile this trend towards lower costs with the kind of deep, with our kind of desire to push MPC and cryptographic protocols as a way to solve collaboration problems. Now, there's been a lot of work in creating MPC frameworks for practical computations, and these have resulted in real improvements, right? We've seen MPC be applied for all sorts of real-world applications to get real data science results that wouldn't be possible without encrypted computation. But MPC has an inherent overhead, right? And there's really nothing we can do about it. And, sometimes this overhead can lead to up to a 100x slowdown. And if you're talking about a pay per hour public cloud, that's 100 times the cost of existing GWAS pipelines. Imagine you're a data scientist with a fixed size NIH grant, you're not going to pay 100 times more, right? So, and there's an interesting study recently. AWS has its own secure computation offering for data science called Clean Rooms, right? So it's a cloud data science offering that incorporates some MPC ideas. And these researchers found that Clean Rooms was as expensive as running the most expensive AWS instance. So there are significant advances in MPC and it's improving slowly, but costs are still an impediment, especially when I'm telling data scientists we want to use MPC. It's a tough sell. So what do we do? Well, what we asked is, how do non-cryptographers reduce cost in the cloud? Right? Because clearly we're not the first people to encounter this. And the answer is spot instances. So if you're not familiar, a spot instance is a special type of cloud virtual machine instance. What you do is you set a bid price. This is how much you're willing to pay for the instance. And there's a spot price that varies over time. Basically, if the cloud has excess capacity, the price of the spot instance goes down. Once a spot instance goes below your bid price, the spot instance is now live. So you can see now there's a spot instance lifetime. But the moment that the spot instance price goes beyond your bid price, for instance, a lot of people want that type of instance, and they're willing to pay full price for it, you will get a revocation notice. So a revocation notice means your spot instance is going to be shut down because it needs to be used for the hardware resources need to be used for someone else. So what's interesting about this is that it's a very short turnaround. It's as low as 30 seconds So within 30 seconds, you need to be able to shut down your resource use. Now, on the other hand, spot instances offer significant cost savings. If you are able to use them, you can get up to 90% off the listed price of a computation. And there's a lot of examples of companies using spot instances to their advantage. I really like football, and they always talk about how the NFL uses spot instances to reduce their costs. But beyond kind of the corporate entities, you've actually seen bioinformatics genomicists use spot instances to reduce costs. So this is a paper that was recently published, and they specifically mention spot instances as their computation model so they can reduce the cost of their GWAS computation. So, okay, so maybe we can just use spot instances with our MPC. Now that kind of seems like the path forward that starts to appear. But a new issue kind of arises because now we're having these instances that can go on and offline really at a whim, and we're trying to incorporate that with MPC. Well, most traditional MPC protocols and implementations consider fixed parties, right? So it assumes that the three parties here, for instance, that are computing MPC are always online for the entirety of the computation. But if these parties are spot instances and one of them gets revoked for some reason, right, then we don't actually have a good way of modeling this in a traditional MPC protocol, right? This kind of dynamism introduces additional complexity, and it requires some careful consideration for the security of the model, right? So how do we recover from preemption, right? How do we recover from a spot instance being revoked, right? We need some kind of preemption tolerance mechanism. And to do that, we can actually turn to inspiration from the systems community. Okay, so let's rewind a little bit. What do we want to do? We want to leverage spot instances for our MPC. We want to tolerate preemption, and we want to do so in an MPC native way that doesn't give up any security. So how do we do this? So one thing we can do we want some kind of, like this third point, this MPC native point. How do we achieve this? So we can turn to something called Fluid MPC. And Fluid MPC creates a model of multi-party computation where parties can enter and leave a computation in the middle of the computation, right? So this is kind of general now research area called dynamic MPC. After a round of computation, I can kind of leave and move. So this has mostly been studied in theory. That really hasn't been studied in a practical setting quite yet. But this has an interesting kind of approach. Like we can kind of say, oh, well, I'm running, but then my spot instance is going to go down. Maybe I can hand off or migrate my runtime instance state to another node that's running. Now, an interesting thing here is dynamic MPC, like I said, is theoretical and focuses on rounds. So after one round of computation, I can hand off. But a spot instance preemption may happen at any time, right? It can happen even within a round, while before a round completes. So bringing this dynamic MPC into a practical framework is part of the contribution of our work. Okay, so let's work through an example just so you get some little more intuition on how we're going to do this migration. The first round, we have some spot instance running 1, 2, 3, these three clients. And let's say that client 2 receives a notification that it's going to be revoked or preempted. So that means client 1 and client 2 will proceed into the next round as normal, but client 2 will now have to be migrated. So we're going to have to migrate client 2 to a new node. So we're going to take the state that was running in round 1 on client 2 and move it to a new spot instance that's running. And then we can continue round 2 as before. Now client 2 is logically on a different instance, but we can continue our protocol and keep it going. So, this can keep going. Like let's say in the next, while round 2 is happening, we receive a preemption notice for clients 1 and 3. Then we perform a migration to new instances. And then we can proceed with the next round. So this kind of idea is kind of intuitive. It's really just adding a layer of fault tolerance on top of the MPC protocol. Now, there are obviously some details here, right? The migration system is reactive, so we need to be able to account for revocation windows. I said that you only have 30 seconds, so something that we'll have to evaluate later is that the migration occurs within these 30 seconds. Now, another thing is how do we actually achieve the security of the migration? So what we do is we do this thing called re-randomization. So when I hand off my state, I engage in a protocol that re-randomizes the share state so that the new node, the next node, has a completely different set of shares than I was running in my original computation. So this allows for an extra layer of security so that this next set of node can't necessarily rewind the protocol or do some kind of malicious activity with the fact that they have my previous state. And there's some more details here that I won't get into, but the Fluid MPC paper talks about this, and the core of it actually goes back to a protocol called GRR, which coincidentally, or not so coincidentally, one of our co-authors, Rosario Gennaro, was an author of back in the 90s, early 2000s. So another thing that we do is I explained here that spot instances hand off to other spot instances. But sometimes you might not be able to allocate a new spot instance that's within the 30-second window. Maybe you require some more time to allocate a spot instance because that's actually up to AWS or the provider to handle that. So what we have is an army of substitutes. So these are low compute nodes that are always running in the background. These are on demand and won't be preempted. But we try to find the cheapest node possible. What we do is if a new spot instance can't come up in time, we're going to hand off to a substitute. The substitute will then continue the computation on behalf of the original client. When a new spot instance is available, we'll hand off back to the new spot instance. And by doing this, we can allow the protocol to continue in a structured fashion without it kind of blocking or jamming if a new spot instance can't show up. And we emphasize that these are very cheap nodes because they're only meant to support the spot instance transition and nothing more. We also implement our own circuit design abstraction. I mentioned this idea of handing off and migrating. It doesn't really line up with the traditional MPC protocol. And like I said, that this dynamic MPC idea has mostly been discussed in theory, so we actually had to do a little bit of our own development to make sure that the semantics can be encoded into an MPC circuit that's actually computed. So we have some handoff primitives that we created inside of every MPC circuit inside of our ThriftyMPC system. And what we do, it organizes our computation into granular compute units. So here's an example of our domain-specific language. We build it based off of Rust. And you can kind of see there's this call in the middle to builder.handoff, which basically tells the circuit builder that, hey, everything before this point up to the last handoff point is kind of an atomic unit. So this allows the circuit writer, the person who's writing the actual MPC, to encode where they think handoffs should or should not be allowed. So migration is an interesting model, and it is rooted in something that we've seen in a cryptography with dynamic MPC, theoretical cryptography with dynamic MPC. But what about a different approach? What about one that's a little bit more proactive, right? What if we have a way to proactively save state rather than migrating it the moment we find out that there's a spot instance revocation? That way, we don't have to worry about revocation windows. We don't have to worry about breaking up circuit layers into atomic chunks. And this is where the thing I mentioned earlier about taking inspiration from the systems community comes in. Because the systems community has built these very fault-tolerant systems, resilient systems on top of unreliable spot instances. So this is one such paper from the 2010s that does just that. They build such a system on top of spot instances. And one of the systems that they provide, one of the systems that, or excuse me, preemption tolerance mechanisms they provide is known as checkpointing, which we also integrate into MPC. And checkpointing is also an intuitive idea. And now instead of migration at the end of a round, what we're going to do is before a round, we're going to save state. So we have some cloud storage like AWS S3 or OpenStack Swift, and we're going to record all of our computation state into this cloud storage. Now let's say migration happens, revocation happens. So to this second client here. The first and third clients are going to proceed the same, but now we have a new spot instance that has to come online for this previous instance. So what we're going to do is we're going to take our cloud storage and use it to retrieve the previous computation state and then continue the protocol. Now, because this is proactive, I've recorded my state before a round. I have to repeat the round. So I have to repeat round 1, for instance. But then the protocol can then continue. And similarly, in future rounds, I'm going to perform save operations. And if I need to, I can recover previous computation state from this cloud storage local to each client. So this is an alternative mechanism. The security properties are a little bit different. Our paper has more details, but this proactive mechanism prevents this reactive migration style requirements, and actually, as we'll see later, results in some additional cost savings. So that is the overview of our system, which we call ThriftyMPC. Our service provider is some cloud provider, and all we require them to do is provide the preemption notices over these spot instances, allow us to procure new instances as necessary. Then the data holders can use our system and share inputs amongst each other. Now, the two mechanisms are slightly different. Migration has this idea that we're going to reactively send off to other spot instances or substitutes. Checkpointing involves saving or caching state to cloud storage, persisting it over time. We do note that for both of these mechanisms, we have a coordinator, which is a long-lived node that helps the protocol move forward, retain state. It doesn't have any secret information. It's really just a bookkeeping thing. There are ways to remove this coordinator with some more MPC if you'd like, but we find that having a coordinator helps simplify the implementation. Okay, so with this in mind, the next question is, how do we evaluate it, right? So initially, to evaluate it, we use the Jetstream 2 platform, which is actually a research cloud platform that we got access to through the NSF Access program. And if y'all haven't used this before, I would highly recommend it. It provides free cloud computing to folks at US institutions for their research. And this allowed us to rapidly prototype and test our system in something that looked very much like a real cloud without having to pay real cloud prices. But next, we moved to a live test bed on the Google Cloud Platform, where we actually ran ThriftyMPC on real instances to figure out how well that our protocol would perform. And we tried to get the types of instances, both on demand and spot, that would reflect what real data scientists would use for their computations. So speaking of real data scientists, what example application did we use? We use a genome-wide association study, like I talked about at the top of the talk. But we don't use any real data. We use simulated data rather than actual biobank data. And part of this is a reproducibility concern. We want future researchers to be able to reproduce our results easily. Some of the actual human biobank data have restrictions on the use of data that would prevent us from being able to perform like a purely reproducible study. And obviously there's ethical concerns around using real human data. But one thing that we hope to do in the future is to use real human data to see if our setup can actually perform an interesting analysis. But the simulated data has the same structure as human data. And the specific study I'll mention too is we use the Cochrane-Armitage test, which is a common test in GWAS that performs this association between diseases and genetic mutations. So the baseline we compare against is something called MP-SPDZ. It's a state-of-the-art MPC framework. It's highly optimized. And we use it to kind of show how our system compares both in terms of runtime, classical runtime and communication factors, but also cost. Okay, so let's get how fast is ThriftyMPC compared to the baseline. Okay, so I mentioned that MP-SPDZ is highly optimized, has offline preprocessing, lots of really cool optimizations. So you can see here the runtime of ThriftyMPC, especially at large sample sizes, is much larger than the runtime of MP-SPDZ at equivalent configuration. So each sample here has about 600,000 single nucleotide polymorphisms that are being computed. And what's interesting with this chart is if you scale it up to a real human genome study, something that would actually take place in a traditional bioinformatics setting, MP-SPDZ would take about 15 days to compute this to compute all of the GWAS stuff. And then at this kind of if we kind of extrapolate everything out, then ThriftyMPC would take 33 days. So, we really showed like ThriftyMPC is really not optimized, right? Up to twice as slow. It's not so great in terms of pure optimization on runtime. Okay, so let's put a pin in this. We'll come back to this. The next thing I want to ask is how expensive is preemption tolerance, right? So spot instances provide some discount, but we need to be able to have a fault tolerance layer on top of it so that we can keep the MPC going. So we basically measured how long it takes to perform this handoff of with both the migration setting and the checkpointing setting. So the migration setting in the brown, you can see just scales with the sample size. It makes sense. The more data you have to hand off, the longer it takes. But the checkpointing thing you can see here takes a little bit longer, but it's a little more stable as the sample size increases because we're sending data out to storage. But generally speaking, both things are pretty quick. Both saving something to a checkpoint and loading a state from that checkpoint, as well as migration, is less than 5 seconds even at a 9,000 sample size, which is pretty good. But now let's come back to that original point about comparison to MP-SPDZ. Let's put everything together. How much money can we save, right? We wanted to make large-scale cloud-assisted MPC cost-effective. So here is our chart. And we can see here the green is MP-SPDZ on demand. The blue with circle is reactive migration, and the red squares are proactive checkpointing. So we can see that despite being up to twice as fast as our MPC or MP-SPDZ baseline, it's still MP-SPDZ costs way more because MP-SPDZ cannot incorporate these preemption tolerance mechanisms. It can't use spot instances. But the fact that we can use spot instances gives us about 80% cost reduction depending on your sample size, which is really good, right? Now, there's a difference between migration and checkpointing that you can see as the sample size increases. I mentioned earlier the security is a little different. Reactive migration has a stronger model that's closer to what theoreticians prefer for dynamic MPC, but there's like a trade-off that you can make if you want to save a little bit more money. With the checkpointing, you can. But I do think that the results show that cost-effective MPC is possible in practice, right? Even comparing against this really optimized baseline where we really don't perform any of these optimizations, we still can achieve a very strong result. So what do we learn from all of this, right? So, approaches in the dynamic MPC literature can be used in practice to leverage spot instances for MPC, right? So this theoretical model can actually be used to build a highly optimized MPC system that is cost effective, or highly cost optimized MPC systems, I should say. And regardless of whatever preemption tolerance approach we take, we show a significant cost savings that can be realized, even over optimized systems like MP-SPDZ. And finally, ThriftyMPC is really agnostic to the underlying MPC scheme. I want to point out that we built our system and wrote a lot of it mostly because dynamic MPC hasn't been studied in practice. But we can imagine if we had all of the kind of prior knowledge of optimizations of MP-SPDZ integrated with these preemption tolerance mechanisms, we could achieve some serious cost savings. So it's really just a framework, a way of thinking about fault tolerance for MPC. So what does this tell us about cryptographic hardware? right? Why am I telling the Cryptolets community about this? Right? I do think that something that is missed a lot in cryptographic deployments is that cost is an important factor, right? When we're trying to develop things, we need to make sure the end-to-end deployment is going to be cheaper than the status quo. Runtime gains are not necessarily improved costs, right? We saw that MP speeds was so much faster, but more expensive. So considering like how does the hardware interact with the cost incentives for secure computation is a really important factor to consider. I also think it's important to have good benchmarks for evaluation. Like were lucky enough to work with the genomicist on our work and source on benchmarks that tie back to the application we want to do. We were able to get richer outputs than just a random function evaluation like prior work. And in developing that, we were able to identify bottlenecks that were necessary to overcome if we want to get something like this actually deployed. And finally, I think we need to think about systems end-to-end if we want cryptography to be deployed. ThriftyMPC takes into consideration the protocol, the deployment environment, the application user needs. I think the missing step is the hardware, right? And I think primitive development is important at all layers of the stack, but for a real deployment, we need to think critically about the composition of everything and how each layer impacts the next. So with that, I will conclude my talk. My contact information is here. Please take a look at our preprint if you're interested, and I'm happy to take your questions.
Any questions for Tushar? I have one while you guys are thinking about that. Tushar, back on slide 23,
Uh-huh.
those two charts look exactly the same. Could you tell me how they differ?
Yeah. So essentially what this are the difference is the number of revocations that happen. We call them handoffs in our paper.
Mhm.
And basically what you can see is the revocation does not actually have a measurable impact on the cost, is what these charts are saying.
That's what it says. Yeah, interesting.
Yeah. So, that means that these revocations are being handled so quickly that we don't actually have a material runtime increase. So,
Great. Thank you.
yeah.
Any other questions? Very good. Well, thank you, Tushar. I think that will conclude our session. We will be posting this video on the cryptolets.org website. So if you would like to see it again or refer to your colleagues, please point to cryptolets.org.
Thanks, everyone. Thanks, Warren. Take care.
Take care. Bye.
Bye.